Salam, peace be upon you. My name is Mohammed Layiq Sediqi, the father of Holophase. Part 17. Phi operating system, running many dreams. Remember the language we are learning. There is one field, phi, the holophase, one continuous cyclic movement from which all of reality unfolds. When phi begins to change, its first derivatives appear, and with them, the three dimensions show themselves at once. Time as omega, space as k, and motion as v, built from both. Every higher derivative is a finer question about how phi changes, and each one casts three shadows together: a time shadow, a space shadow, and the motion shadow. These echoes mix and weave into one another, forming the patterns we call fields, particles, bodies, thoughts, and worlds. In this picture, everything that exists is a living tapestry of phi, endlessly echoing through its derivatives and their dimensional shadows. Today, we listen to just one of those echoes.
We are in the heart of TAM, Book 10.3, Phi Programming. We have learned to write a single intention. We have mastered the debugging loop for one process. Now, we face the challenge of scale. A single foundry is a precious resource, a cathedral of coherent control. What happens when 10, 100, 1,000 dreamers wish to use it? What happens when one program must run alongside another? When a sensor scan must not disturb a delicate material growth? When a city's traffic flow must coexist with its energy grid's resonance? We cannot have chaos. We need governance. We need an operating system. We leave the single program diagnostic chamber and enter the mission control center. Rows of consoles display the health of dozens of concurrent phi processes. A central hologram shows the foundry's total phi field, a living mosaic of many dreams, carefully kept from bleeding into one another. Your new skill is that of the systems architect. You are learning to design the rules, the partitions, the schedulers that allow many minds to co-create within one coherent substrate. Scene: the Mission Control Center. The air is cool, filled with the soft chime of status updates and the low hum of massive computation. Before you, the main hologram depicts the foundry's active volume. It is not a single scene, but a patchwork of realities. In one quadrant, a crystalline lattice is slowly growing, its phi field a perfect, expanding hexagon. In another, a turbulent fluid simulation churns, a research program studying vortex dynamics. Along the edges, faint scanning waves pulse, the background sensor suite, the foundry's own immune system, constantly taking its health vitals. Thin, shimmering walls of light separate these regions. These are not physical barriers, but firewalls, enforced phase gradients that say to the field, "Thou shalt not pass." Your console is a master overview. You see not code, but resource allocations, coherence budgets consumed, topological charge quotas, spatial slices assigned, time slices scheduled. This is the dashboard of a shared reality. Our puzzle? How do we manage the finite, shared resources of a phi foundry, its coherence, its space, its capacity for topological complexity, among many concurrent, potentially conflicting processes, while guaranteeing each one's integrity and the system's overall stability? The language role, the systems management skill. This part teaches a control skill at the systems level. It is the skill of orchestrating coherence among multiple simultaneous manipulations of the phi field. Our core question about phi is, given a single continuous phi field, the foundry substrate, and multiple independent programs wishing to edit it, how do we partition, schedule, and isolate these intentions so that each achieves its coherent goal without destructive interference? We are moving from writing solo performances to conducting a symphony. The anchor image, the air traffic control tower. We will use the anchor image of an air traffic control tower. The foundry's airspace is the phi field. Each program is an aircraft with a flight plan, its code. The OS is the control tower. Its jobs are assign takeoff landing slots, scheduling, assign flight paths and altitudes, spatial partitioning, ensure planes don't collide, isolation, monitor fuel and weather, resource accounting, and have emergency protocols, safety rails. The shared resource is the sky. The goal is maximum safe throughput. The coherent selection principle in systems. In a multiprocess system, coherence becomes a multi-layered concept. Constructive resonance, alignment, now means each process maintains its internal coherence, and the OS's management creates a meta-coherence, where processes coexist without degrading each other. the whole system is stable. Destructive resonance, dissonance, means one process's patterns leak into another's domain, causing interference, decay, or outright annihilation of a pattern. Or the combined load destabilizes the foundational field of the foundry itself. The system's mantra remains: if coherence breaks, we stop. If coherence returns, we continue. But now, coherence breaks could be in any process. If one process goes unstable, the OS must contain it before it crashes the others. The core mechanisms: resource accounting, scheduling, and isolation. A FI-OS has three fundamental jobs. 1. Resource accounting, the ledger of reality.
The foundry's capabilities are finite. The OS must measure and limit. Not just per program, but a total system coherence capacity. How much total intensity of change can the foundry's field sustain before it becomes noisy or unstable? Each process is allocated a slice. The OS tallies this in real time. Topological charge quotas. Creating defects costs topological energy and changes the global constraint landscape. The OS sets a system-wide limit on total net charge, or allocates charge quotas to processes. A process cannot inject defect if it would exceed its quota. Spatial allocation. The foundry has a finite volume. Processes request spatial regions. The OS acts as a real estate manager, ensuring no two processes are allocated overlapping space unless they explicitly opt into sharing and have compatible constraints. Temporal allocation. Compute actuation time. The foundry's actuators and solvers can only do so much per second. The OS schedules time slices. 2. Scheduling algorithms, the conductor's baton. How does the OS decide when and where each process runs? Time slicing. The OS gives each process a short, alternating turn to advance its simulation or actuation by one step. This is like a CPU sharing its core. It works well for processes that don't need constant, real-time interaction with the field. Spatial partitioning. The OS carves the foundry's volume into non-overlapping domains, like apartments in a building. Each process gets its own apartment to decorate as it wishes. This is perfect for isolation. Frequency division multiplexing. For wave-like processes, the OS can assign different frequency bands. Process A uses omega between 1 to 2 Hz. Process B uses 3 to 4 Hz. The phi field can carry both simultaneously, just as air can carry many sound waves. The OS enforces the filters. 3. Isolation and sandboxing, the φ-firewalls. This is the most critical mechanism. How do you stop a turbulent fluid in quadrant A from messing up a delicate crystal in quadrant B? Phase spinning regions. You create a buffer zone, a wall. In this zone, you impose bordered with a very strong pinning potential, locking phi to a fixed value or gradient. This creates a high-energy barrier for phase slips or defects. It's a phase insulator. Constrained boundary enforcement. At the firewall, the OS actively runs a microprocess that continuously corrects any deviation from the desired insulating condition. It's like a guard constantly repainting the line. Information theoretic sandboxing. For ultimate safety, a process can be run in a complete digital twin sandbox that is logically part of the foundry but physically isolated. Its outputs are only reintegrated after verification and filtering. The coherence budget. System-wide stability thresholds. Before allowing multiple processes, the OS sets a system-wide coherence budget. 1. Total coherence load. The sum of all processes' allocated coherence budgets must be less than the foundry's maximum stable coherence capacity. This capacity is measured experimentally. At what total change intensity does the foundational phi field start showing system-wide noise or instability? We operate at, say, 70% of that limit to keep a safety margin. 2. We define a maximum allowable leakage between processes. This is measured by running two benign, stable processes in adjacent partitions and measuring the unwanted phi fluence, the amount of change that sneaks through the firewall. This defines our isolation performance budget. 3. Rollback resource budget. The OS must always reserve enough spare coherence capacity and spatial scratch space to execute an emergency rollback of any single process. You cannot be so fully booked that you have no room to contain a failure. The budget rule. The OS must refuse to admit or start a new process if doing so would violate any of these system-wide stability thresholds.
The coherence gate and rollback trigger. The coherence gate is monitored continuously for every process and for the system as a whole. What we measure. Per process, internal stability metrics, error from its own target, defect stability. Interprocess, crosstalk metrics at firewall boundaries. System-wide, foundational field noise, total coherence load. Pass rule, system coherence gate. All per process metrics are within spec. Crosstalk is below tolerance, system noise is low. The system passes, operations continue. Fail rule. Any one process exceeds its internal error tolerance due to external influence, or crosstalk exceeds tolerance, or system noise spikes. System coherence is breaking. The rollback trigger is multi-level. Process level rollback. If a single process goes unstable internally, its own bug, the OS freezes it, reverts its allocated region to a previous good state, and notifies its owner. Other processes continue. Containment level rollback. If a process threatens others, high crosstalk trying to exceed quotas aggressively, the OS isolates and throttles it. It strengthens the firewalls around it, reduces its time slices, and may freeze it. System-wide rollback. If system-wide metrics fail, this is a red alert. The OS initiates a graceful degradation. It pauses all non-critical processes, like research sins, saves their states, and powers down their regions, freeing coherence capacity. Only core critical processes, sensors, life support for biological experiments, remain. This is the equivalent of safe mode. A measurement scene, the sensor and the sculptor. Let's enact our roadmap's measurement scene. Scene, a foundry running a constant background sensor scan. Process A, a gentle sweeping plane wave to probe field integrity, while a user runs a delicate material growth program. Process B, slowly aligning molecular dipoles into a crystal. Both complete successfully with zero interference. Setup without OS. Both programs run raw on the same field. The sensor wave passes through the growth region. It adds a tiny oscillating perturbation to the phase. This acts as noise for the growth program. The crystal grows with defects aligned to the sensor frequency. The sensor readings from the growth region are distorted by the changing material. Both outputs are corrupted, fail. Setup with OS, the pass. Spatial partitioning. The OS allocates the growth program a dedicated interior region. The sensor scan is allocated the complementary region, everywhere except the growth volume. Firewall. At the boundary of the growth region, the OS imposes a phase-pinning firewall. The sensor wave reflects off this wall, unable to penetrate. Resource quotas. The growth program has a high coherence budget for precise alignment. The sensor has a low, fixed budget for its gentle scan. Rotations. Execution. The processes run. The sensor scan operates flawlessly in its domain. The growth occurs in perfect silence, isolated from the scanning rhythm. The final crystal is defect-free per its spec. The sensor data shows a clean baseline everywhere, with a flat line, the firewall, at the growth region boundary. Pass. The coherence gate is open. The fail path. Isolation failure. What if the firewall is too weak? The sensor wave partially tunnels through. The growth crystal shows a faint, periodic striation pattern. The sensor data shows faint echoes from the crystal interior. Crosstalk metrics are above tolerance. The OS detects this, triggers a containment level rollback. It strengthens the firewall, increases pinning potential, and may restart the growth process from a checkpoint before the interference began. The prediction spine, the hallmarks of a good OS. A well-designed FiOS yields a powerful prediction spine. 1. Increased throughput. Under a well-designed OS, total foundry throughput, successful program completions per unit time, will be higher than in an unmanaged first-come, first-served system where conflicts cause frequent crashes and restarts. 2. Near-zero conflict failures. The failure rate of processes due to inter-process conflict, crashes, corrupted outputs, will drop to near zero. Failures will only come from internal program bugs, which are then contained. 3. Deterministic reproducibility. System behavior becomes predictable and reproducible regardless of the order in which processes are submitted. The OS abstracts away the chaos of contention. If program X works at 2 p.m. alone, it will work identically at 4 p.m. alongside programs Y and Z because the OS guarantees it the same isolated resources. Falsifiability when sharing is impossible. Our falsifiability threads test the very possibility of a shared reality substrate. If, despite every ingenious scheme, no isolation method can prevent a malicious or buggy process from crashing other processes or the OS itself, if influence always leaks in some unpredictable way, then scalable, shared fee computing is impossible. Foundries would be single-user, single-purpose devices. Civilization-scale collaboration on reality editing would be infeasible. This would be a profound limitation. If the overhead of the OS, the coherence cost of maintaining firewalls, the computational cost of scheduling and accounting, consistently consumes more resources, coherence, space, time, than it saves by enabling sharing, then the OS is not viable. It would be more efficient to just have many small single-purpose foundries. The economies of scale wouldn't materialize. These falsifiers keep us grounded. Can we truly build a shared sandbox for reality, or is reality inherently solitary? Triunity in the operating system. The OS manages triunity at a meta level. Time echo scheduling. Time slicing, real-time scheduling, process lifecycle, start, pause, stop. This is the temporal orchestration of many dreams. Space echo, partitioning. Spatial allocation, firewall geometry, region shapes. This is the spatial cartography of the shared field. Motion echo, interference management. The OS must manage the motion of influence, the flow of coherence from one region to another, the drift of defects, the propagation of waves. Its firewalls are designed to stop or guide these motions to prevent collisions. A robust OS is a dynamic triune entity that itself has a timescale, scheduling cycles, a space, the foundry map, and a motion, the flow of control decisions. Lanterns across scales, the OS of everything. This is not just for lab foundries. It is the pattern for any shared resource in a file-literate civilization. Near-scale cellular OS. Imagine a biological cell as a foundry. Different organelles run different programs, metabolic pathways, protein synthesis. The cell membrane and internal membranes are biochemical firewalls, allowing selective transport. The cell's OS allocates energy, ATP budget, and building blocks. Understanding this as a FiOS could revolutionize synthetic biology. Middle-scale urban OS. A city is a foundry of people, vehicles, and energy. The traffic light network is a scheduler. Zoning laws are spatial partitions. The power grid stability protocols are coherence budgets. Frequency and voltage must stay within bounds. An urban FiOS would dynamically adjust these in response to real-time Fi sensor data, crowd flow, energy demand, to optimize total well-being. Managing Earth's climate, biosphere, and human economies is the ultimate OS challenge. Carbon budgets are coherence quotas. Protected ecological zones are spatial partitions with firewalls, limited human interference. International treaties are scheduling agreements for resource use. A planetary FiOS would be the implementation of Book 10.8's stewardship institutions. The ethics of the OS. Fairness and containment as law. The ethics of an operating system is the ethics of governance and resource allocation. 1. Fairness as a scheduling policy. The OS must have transparent, fair policies for allocating resources. Is it first come, first serve? Priority-based? Market-based? Bidding coherence credits? The choice encodes a social contract. This is where Phi economy 10.7.1 begins. 2. Containment as the prime directive. The OS's most sacred duty is containment. A bug in one user's crystal growth must not ever, under any circumstances, destabilize another user's long-term ecosystem simulation or a hospital's biomedical sensor array. This is non-negotiable. The firewall is the embodiment of the right to exist undisturbed. 3. Auditability via the resource ledger. Every allocation, every firewall rule, every rollback is logged in an immutable ledger. This provides perfect accountability. If a process failed, was it its own bug, or did the OS give it insufficient resources? The ledger settles the dispute. Power without an OS is anarchy. The OS is the embodiment of the ethic. Your freedom to swing your fist ends where my nose begins, translated into the language of phi fields. The recognition skill, seeing the need for an OS. You know you need the skill when you see contention for a shared physical substrate.
When two researchers want to use the same laser table at the same time. When a new building's Wi-Fi disrupts a neighbor's home network. When watering your lawn affects your neighbor's well level. When one country's pollution becomes another's acid rain. The moment you think, we can't both do this at once without messing each other up, you are facing an OS design problem. The solution is not just negotiation, it's the design of a systematic isolation and scheduling protocol that turns contention into coexistence. The master tree location. This part, 10.3.3, is a major trunk on the master tree. It depends on the debugging branch, 10.3.2. Primer must understand how a single program executes and fails to manage many. It is the crucial bridge between individual programming and collective civilization scale use. It enables the next massive growth, the compiler, 10.3.4, which must now produce code that is OS aware. Networks, 10.5.4, that connect multiple foundries running their own OS instances, and the entire fee economy, 10.7.1, which runs on the OS's resource accounting ledger. This is the foundation for multi-user civilization. Return to the fee. Let us zoom out. The fee field is one, continuous. Our programs are localized intentions within it. The operating system is a meta pattern in the field, a pattern of constraints, firewalls, rhythms, schedules, and accounting, resource tallies, that itself must be coherent. It is a fee structure that manages other fee structures. The universe itself might be seen as running a kind of ultimate OS, with the laws of physics as its immutable kernel, allocating space-time and energy, preventing paradoxical violations. We are learning to build humble, local copies of that principle for our own tiny foundries. Zenodo and the equations of the OS. If you want to see the full mathematical derivations and exact equations behind this idea, you can search for Holophase on Zenodo. There you will find the scientific papers that this audio journey is built on. The papers formalize the resource accounting as constrained optimization problems, derive the stability criteria for phase-binning firewalls from Ginzburg-Landau type equations, prove isolation theorems using information theoretic bounds, and simulate the performance of various scheduling algorithms on model phi dynamics. They provide the rigorous foundation that turns the beautiful concept of a shared reality OS into a buildable, provably safe engineering system. So, picture yourself in the mission control center. The hologram displays a dozen vibrant sub-realities, each pulsing with its own purpose, separated by serene walls of light. A soft chime announces the successful completion of the crystal growth program. Its region dims, and its resources are returned to the pool. Simultaneously, a queuing light blinks. A new process, a complex fluid dynamic study, is admitted. The OS instantly carves out a new region for it, erects fresh firewalls, and allocates it a time slice. The new simulation blossoms into existence, without a ripple disturbing the ongoing sensor scans or the other research running in quiet corners. You have just witnessed the miracle of shared creation. You have learned the principles of the phi operating system, the art of running many dreams on one canvas without letting them become a nightmare. This is part 10.3.3, phi operating system, running many dreams. It is the governance layer of book 10.3, the necessary bridge from individual craft to collaborative civilization. In our next session, we complete the loop. We have a language, a debugging discipline, and an OS to manage execution. Now we need the final translator, the compiler, 10.3.4. We will learn how the clean, high-level intentions of your phi program are transformed into the low-level OS-aware instructions that actually tell the foundry's actuators what to do. We will learn to build the bridge from thought to thing. Remember, one field, phi, with its infinite echoes. We are no longer just speakers or listeners or even conductors. We are now architects of the stage itself, building the shared space where the symphony of creation can safely play. Salam, and peace be upon you.